Okay, so now we're looking at how to get these indeterminate forms into quotient form. So let's look at example 6a, first one. Never not first, right? Direct substitution. If you plug in an infinity, e to the negative infinity approaches what? 0, right? Because it's like 1 over e to the infinity times the square root of infinity is still infinity. So 0 times infinity is not 0, and it's not infinity necessarily. It's a tug of war. So that's an indeterminate form. So this would be the easiest one to get into quotient form. You just got to bring one of the factors to the bottom. Just kind of like I said, bring that to the bottom and get infinity over infinity. Or you can bring the infinity to the bottom and get 0 over 0. So it doesn't matter which one. Which factor, though, is more suitable, perhaps, in this problem to bring to the denominator? The e to the negative x, right? Because it already has a negative exponent. And so if we leave the square root of x on the top and bring the e to the x on the bottom, that would make it kind of nice, very convenient. Now if we use direct substitution, we get the square root of infinity, which is infinity, over e to the infinity, which is infinity. So now it's an indeterminate form. So you can proceed with L'Hopital's rule here, or can you use the big O function? We're going to infinity, yeah, we can. So which one goes faster? The bottom. Okay, so this does go to 0. If you want to verify it with, L'Hopital's rule, I'll let you do that on your own. But if this were a problem on a test, I would still prefer that you did it this way. Okay? All right, letter B. We had this one. Letter B was already done up here when we did it numerically. We were approaching from the right-hand side. We didn't have to be so careful because we did it numerically, and we were only plugging in values to the right of 1. We got an answer of 1/2. So if I were a bad teacher, I would just say, okay, the limit of that is 1/2. Go ahead and memorize that, class. All right, memorize that. I'm a good teacher. I'm telling you to memorize that. And if you ever see that particular integral ever again, you know it's 1/2, right? Go me and go y'all. Teamwork, right? That'd be horrible. So let's see if we can learn a method then that we can apply more generally across the board for any particular problems like that. We've already done direct substitution. We do get infinity over infinity because we're approaching 1 from the right-hand side. Now, that's very important because we already know how important it is for one-side limit. If one of those plugins would have yielded not a positive infinity but a negative infinity, it would be negative infinity, perhaps minus infinity. That's not indeterminate. That's negative infinity. Or if the second one had been negative, minus a negative means plus. Infinity plus infinity is not indeterminate. It's positive infinity. So it's very important that we knew it was a positive infinity and then minus another positive infinity. That makes it indeterminate. So what I need to do now is try to get a difference into a quotient. Any ideas how to do that? Natural logs? Well, we already have a natural log. What do you notice about the two terms individually? Are they already quotients? They're fractions, yeah. There you go. That's the insight. I already have fractions. I just need to get them together into a single fraction. And the way that you combine fractions is to get a common denominator. The natural log of x and x minus 1 are co-prime. They're mutually prime, relatively prime, which means that their common multiple is their product. So you could do it the old-fashioned way. Multiply the first one by x minus 1 over x minus 1. Multiply the second one by ln of x over ln of x. Bless you. Or you could do the crisscross applesauce butterfly multiply method. Okay? Which, that's an easy way to do it. It doesn't always give you the least common denominator, but in this case it will. You have to start in the top left, though, always. Multiply down the diagonal. 1 times x minus 1, you get x minus 1. Then you take the sign of the middle, minus, and then you do the other diagonal, which is natural log of x. And so that's why you have to start in the top. If you don't start in the top and you have a subtraction, subtraction is not commutative, so just start in the top left. And it's all going to be over the product of your two denominators, which is their common denominator. So that's a quick, fast, easy way to do it. All right, so now that we've got it into a single fraction, let us try direct sub again. Maybe we fix the problem. 1 minus 1 is 0. 0 minus the natural log of 1 is 0. So we get 0. Bless you. The bottom we get natural log of 1, which is 0 times 0. That's 0. All right, so we didn't get the answer yet, but we got 0 over 0. That's a quotient form. So now we'll take the derivative of the top and the derivative of the bottom. So we get 1 minus 0 minus 1 over x. That's the top. The bottom, oh my goodness. What rule does the bottom require? The product rule. Good thing we remember the product rule, right? The derivative of f times g is f prime g plus fg prime. F prime g plus fg prime. Two factors means two terms, one at a time. So we go 1 over x times x minus 1 plus natural log of x times the derivative x minus 1 is 1. All right, so now let's try plugging in. Maybe we fixed it. Plug in 1 to the top, you get 1 minus 1, which is 0. And in the bottom, you get 1 times 0, which is 0, plus the natural log of 1, which is 0. We still got 0 over 0. At this point, you might think you're doing it wrong, but are we? No, we're making progress. Notice we had 3 terms in the numerator. Now we have 2. That's making progress. So let's just do it again. Now, if you want, you can simplify the bottom first. Someone last period said, hey, coach, we should distribute the 1 over x into there. And I'm like, okay, that's fine. You could do that. You'd get 1 minus 1 over x. That's fine. That works. I'm going to keep it like that because I'm lazy. And I want to review the product with y'all once again because, as I mentioned back when we learned it, for some reason, the product rule is the number one rule that students tend to mess up. Okay? They get anxious and they take the derivative of both of them at the same time instead of one per term. So I'll leave it like that so we get extra practice. All right, so the numerator, we get 0 minus, and then the derivative of 1 over x. Can you do that in your head? Negative 1 over x is really negative x to the negative first, which when you multiply and subtract gives you 1x to the negative second, or 1 over x squared. If you need to take another line to rewrite it, go for it. All right, now I'm going to do the product rule on the bottom again. 1 over x, again, is x to the negative first. So that's negative 1 over x squared times x minus 1, and then plus 1 over x times the derivative of x minus 1, which is 1. So there's the product rule. And then I got the last term in the bottom, 1 over x, is the derivative of ln of x. You don't really have to simplify this. The only time it's really nice simplifying is when you have like negative exponents and fractional exponents, because it's easier to evaluate when you don't have negative exponents and fractional exponents are put back in radical form. It's just easier to think that way. You have more training. All right, so now let's plug in. We get a 1 over 1, which is a 1. And at this point, you're pretty confident that it's not going to be indeterminate because 1 in the numerator is not a 0 or an infinity. When you plug a 1 into the bottom, you get 1 over 1 times 0, which is 0, plus 1 over 1 plus 1 over 1. Well, that's 1 plus 1, which is 2. And there you go. We got a common denominator, put it into quotient form, did a couple of iterations of L'Hopital, and got our answer. So there you go. So infinity minus infinity is an indeterminate form, and most of the time it's just as simple as getting a common denominator. All right, any questions on those so far? We got the multiplicative variety, bring 1 to the bottom. We got the difference variety, get a common denominator. Now, sometimes we do need logs to come to our rescue. Mr. Merrill wanted to send them in as an emergency crew up here on 6A, or was it? No, it was on 6B. But we've already seen how logs come to the rescue to us, right? For instance, if we're integrating x to the negative first, dx, and we try the power rule, we get x to the 0 divided by 0. This is the only time the power rule doesn't work. Who comes to our rescue? The natural log, right? So logs come to the rescue. Here's another time logs come to the rescue. If I'm trying to find the derivative with respect to x of a times v times c over d times e. Ooh, that's going to be, if those are all variable functions, that is going to be a quotient rule with a triple product rule for the d high and a product rule for the d ho. Yucky, yucky, gross, gross. Guess who comes to our rescue? Logs, right? We would set it equal to y. We would take the natural log of both sides. And remember, that allows us to expand it. The natural log of a plus the natural log of b plus the natural log of c minus the natural log of d minus the natural log of e. And then we would take the derivative of both sides. Okay? What would we call that method? Log diff, right? We called that log diff. Actually, we would have to take the derivative over here at the same time. We would set y equal to the function. All right, so that would be the verb format where you actually have to set the expression equal to y. All right, so logs have come to our rescue a couple times. Let's see if they come to our rescue here. Direct substitution. We've seen this guy already. Let's come back up here. This was like 1 part C, right? This was kind of the funky one. It came out to be 7.389. That was kind of an awkward number, 7.389. Well, I guess we're going to get that again. Let's see why. Direct substitution gives you 1 to the infinite power. So remember, that is indeterminate form because we're not really equaling 1. It's something bigger than 1 that's getting smaller and something that's making it bigger. So now we need to figure out how to make an exponential indeterminate form into a quotient exponential form. It's kind of like log diff. This is an expression we need to evaluate. I'm going to set it equal to y first. Now I'm going to take the natural log of both sides. The natural log of y equals, remember the limit can go anywhere, so I'm just going to keep the limit out front. The natural log of 1 plus 2 over x to the x. So why is that useful? Logs linearize exponential. I could then take that exponent out front on the next line. So let's do that. I get the natural log of y equals the limit as x goes to infinity of x times the natural log of 1 plus 2 over x. All right, so now I got it out of exponential form. It's now in kind of multiplication form. Let's go ahead and try to evaluate the right-hand side by direct substitution. Now, I get infinity times the natural log of 1, which is 0. We're making progress. We went from an exponential indeterminate form to now a multiplicative exponential form. And when we're in a multiplicative exponential form, it's pretty easy to fix, right? All we got to do is bring one of the factors to the denominator. And it doesn't matter which one. You can take either one. Anyone for taking the big, ugly natural log thing to the bottom? That would be the whole thing to the negative first. That's going to make the derivative of that kind of ugly. So x says, I'll go. I'm like, good choice. Glad you volunteered. So an x on the top is an x in the bottom that's equivalent is an x to the negative first. And now we have the natural log of 1 plus, I'll call that 2x to the negative first instead of 2 over x. Just because we're fixing to take the derivative after we verify it's an indeterminate form. Direct substitution now gives you the natural log of 1, which is 0, over 1 over x, as x goes to infinity, also goes to 0. So there you go. I went from exponential by way of log to multiplicative, and now from multiplicative to a division quotient form. And so now I may do L'Hopital's rule. Now here's something that's very different. If this were a log diff problem, I would take the derivative of both sides. This is not a log diff problem. I still have the natural log of y on the left, but I'm evaluating the right side by a process called L'Hopital's rule. So I'm not taking the derivative of both sides. I'm just evaluating the right side by now taking the derivative. So the derivative of the natural log of blob is 1 over the blob, which I'll write back as 1 over 1 plus 2 over x, times the derivative of the blob. Well, the derivative of 1 is 0, and then the derivative of 2x to the negative first is negative 2x to the negative second. I'll just leave it like that, negative 2x to the negative second. So it's a chain rule. 1 over blob, root of the blob. The bottom is just x to the negative first. Its derivative is negative 1x to the negative second. Now notice I am also bringing down my natural log of y each and every time. That is highly recommended because remember, we're trying to evaluate the limit, which is equal to y. And if you don't bring down your natural log of y, you can easily forget at the bottom that it's not equal to y, but rather the natural log of y. Anything good happening on the right-hand side now? Yeah, your x to the negative seconds divide out, and negative over negative is positive, so your negatives divide out. So we're just left with this and a 2. So the denominator is 1, so we could just try evaluating right now. You got the natural log of y equals, and if we plug in what happens to 1 over 1 plus 2 over x? It approaches 1 over 1 plus 0, which is 1, times the only thing that's left is 2. What's 1 times 2? 2. Ha-ha. So if this were a multiple choice question, guess what one of the answer choices would be? 2, right? But 2 is not what we want. We want y. That's equal to the natural log of y. So how do we actually resolve for y? E to the that. We e both sides, exponentiate both sides, and we get y equals e squared. There you go. So e is the irrational number 2.718. What is e squared? I messed it up. Look at that. Oop, can't even delete it right. What is e squared equal to? 7.389. 7.389. That's exactly what we found it to be numerically when we did it on the calculator. Now, if the answer was e to the second, is there anything in the original limit expression that might allude to the fact that it was e to the second? Is there a 2 in there anywhere? Yes, it's right here. Is that 2 the reason it was e squared? In other words, if this were a 3, would the answer be e cubed? You could actually verify it. If this were a 1, would it be e to the first or just e? And the answer to that is yes. Okay? So here's what I want to kind of summarize with, because e is a very important number, and it'll be more important when we get to sequences and series. E is defined to be, right now, the limit as, we go x, as x goes to infinity, of 1 plus 1 over x to the x power. That's the definition of e. In general, e to the x is defined to be the limit as n goes to infinity of 1 plus x over n to the nth power. So if you notice what I did there, I wanted to let x be my variable, so I changed the variable x from above to n, and I let n go to infinity. So whatever this number is here, whether it's a 1, a 2, a 3, and the one we just did, it was a 2, it's equal to e squared. All right? So e is a remarkable number. This is its definition. Remember, it's an irrational number, like pi. Later on, you're also going to learn that e is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... The pattern will continue. That's another way to get the exact value of e, which doesn't really have an exact value because it's irrational. So anyway, there you go. Kind of neat. All right, it's 1:08. Any questions so far? Should we do one more? Yeah, let's do one more. Kind of lock it in there. 7b. The limit as x goes to 0 from the right-hand side. We've got to be careful. Of the a left function, what does direct substitution give you? 0 to the 0 power. Is that 0 or is that 1? It's indeterminate. Good. Here's why it's indeterminate. Anything to the 0 power is 1 except 0. 0 times anything is 0. Right? So there's a tug of war. 0 times anything is 0, but anything to the 0 power is 1. So is this answer 0 or is it 1? Is it 0? Is it 1? There's a tug of war. So this is indeterminate. All right, so it's an exponential form, so guess what we have to do? We have to log it. Now again, because it's an expression, we set it equal to y, and in the end we're trying to find y. So we'll do this one kind of quickly here. We get the natural log of y equals the limit as x goes to 0 from the right of the natural log of x to the x. Now I'm going to skip a step, and I'm going to animate it, right? The natural log of x to the x, watch this. Circle the x, lasso it with scissors, bring it out front, whoop, there it is. Okay, now direct substitution. If you plug in a 0 for x, you get 0 times. What is the limit as x goes to 0 from the right of ln of x? it's negative infinity, right? There's a vertical asymptote there. So what's 0 times infinity? Indeterminate, right? So now it's the multiplicative variety. So again, we get to choose which one we want to bring to the denominator. What do you want to bring to the denominator? The ln of x? Yeah? I would not. You try it that way. I'll try it the other way. And we should get the same answer. You just might get there a couple days from now. Yeah, so always try to make it easy. Take the simpler looking function to the bottom. All right, so now if you plugged in, the limit as x goes to infinity from the right is negative infinity. And 1 over x, if you remember 1 over x looks like that. As you approach 0 from the right, it's approaching positive infinity. But it doesn't matter what the sign is. We've got infinity over infinity, which is a quotient version of the indeterminate form. So now we are able to use L'Hopital's rule. So natural log of y stays natural log of y. Not doing log diff here. The limit as x goes to 0 from the right. ln of x is 1 over x. Or I'm going to write that as, yeah, I'll leave it as 1 over x. Why not? And then the derivative of the bottom is negative x to the negative second, which is negative 1 over x squared. So don't forget to clean up a little bit before you evaluate, especially when you have powers of x. So if you stay change flip, you get 1 over x times negative x squared over 1. And I'll go one more line, just rewriting it. One of the x's divides out, right? So you're just left with negative x. Is that right? X squared over x, negative x. And now direct substitution. Plug in a 0 from the right-hand side of 0. Should be okay. Negative x. What is it equal to? 0. Positive or negative 0? Yeah, it doesn't matter, right? We are approaching, here's what 1 over x looks like. It's that line. And we're approaching 0 from the right-hand side of 0. So we're approaching 0 from the negative side, but we don't have to be as careful here because 0 is signless, unlike the possibility. All right, so a multiple choice answer for sure would be 0. We're not the foolish people that are going to forget to bring down the ln of y each time. Because it's there in our face, each and every line, we know that that's not equal to y. We'll e it at the end, and we get y is equal to e to the 0, which of course is equal to 1. So there you go. In this case, 0 to the 0 did in fact equal 1. 5 to the 0 is 1, 7 to the 0 is 1, 10 to the 0 is 1. Is 0 to the 0 always 1? No. But in this case, it was. In this case, it happened to be. Oh, not really. If we're coming from the left side, it would still be 0. Yeah. The only time it's important is if you're like approaching a non-zero value or in infinity, some type of infinity. All right, cool. We'll stop right there. Have a fantastic rest of National Pig Day. Oink, oink.